Hi friends, this is Radhakrishna, and in this video we'll discover how satellites and satellite images or satellite data in general is used in military domains. Oh, I'm sure that most of you must have already heard and come across stories in movies that militaries use satellites, and there's lots of technicality to it, and then there's lots of interesting stuff behind it as well. And almost everything that I'll tell you is declassified information from across the world. If you're thinking enough to connect the dots, you can connect the dots. So military use cases in space actually started with balloons. People started to put cameras in balloons and even kites and try to observe what is happening around them. The major, spying kind of thing happened with the series of missions called Discover or / Corona. Data is declassified now. The interesting thing to Corona is the orbit that satellite does. Usually we call polar orbiting satellites, right? That was actually getting developed in the engineering way when the Corona program started, and this is by the US government. So when the Corona program started, satellites were being engineered to put into orbits, get them repeat, etc. Also today how satellites work is we have payloads inside satellite. When they take an image, they send it to a computer. The computer sends that image as packets through radio frequency antennas, and we have ground stations which can even detect feeble signals and then make sense out of it. Then there was no such thing as ground station telemetry and computers as such. It was like 1960s or something. You can launch a mechanical vehicle that may be called satellite if it is rotating around Earth. So what people used to do was they used to put cameras, which were having films. By the way, if you don't know films and if you're a new generation kid, films were material. When you click an image, the light fell on the film and it recorded what the light was at that particular point of time. Everything related to chemistry. So when that film was developed, someone on ground had to see this, right? So people used to put these cameras with film on satellites, and how people saw the data is by literally bringing the camera and the film down, right? So this is what spying literally meant in those days. So you send a satellite, it rotates around the Earth, and then you bring that satellite down, analyze the data, and see, okay, this is what's happening. And this is what Corona mission also did. So we'll see a couple of images which are really interesting for me, because in the early days I came across this Corona images which were declassified, and I learned a lot of satellite image processing, especially on this Corona images, because it is really interesting, because these films, right, they don't have any Earth information encoded with them. So you need to kind of make sense of what that film is actually seeing on ground and what is actually happening on ground. And mind you, this is data from 1972, the year I think when my mom was born. So very old data. And this data is scanned and it's already open. So what you're seeing on screen is there are two images here, which are basically two different cameras that are put on the same satellite. One camera is looking in one angle, the other camera is looking in another angle, and these are called stereo images. Okay, so they are looking at, let's say, same area with different angles as the satellite moves, and because of parallax effect, you can actually make a 3D image. Okay, but let's not get into all that. Let's just see how the satellite this image looks, right? So this is A and this is C. Both of them are satellite images. So this is how the image looked, and if you can observe here, this is basically a scanned copy of a film, right? So if you know the movie films, right, how movies worked, there used to be a film and you project it. It's the same thing, right? Except that there's a telescope on a satellite which wants to look. And you can see here, this is like a scanned copy. It's showing you, it's captured on 31st May 1972 with an aft camera. The resolution of this, as I see in the documents, is 12 meters. Today's satellite can image without all this, like films and all, at 30 centimeters, right? And that is obvious because the computers have grown and sensors have grown and optics has grown, so on and so forth. Even satellite technology has grown. But you could see people inventing technologies to actually observe what other countries were doing. And this is from Corona of 1972. So you know what US government probably was looking at. But yeah, so, and see, these are hilly images, right? There are lots of hills and paths to get on a hill. And if you wanted a 3D image for this, you basically take another angle image and then you apply photogrammetry and then you get the 3D data. So this is what initial phases of spying look like, and this is from a Corona series of satellites. But the instrument that the program that inside the Corona, it was called as Keyhole. Okay, and it is, I think, KH1. So Corona is the series of satellites, KH1 is the payload, Keyhole 1. And this name Keyhole is also basically because of spying. So in a door you have a keyhole, right? And from the keyhole you can see what's happening inside the room or whatever. So this is basically from that. And KH1 meaning initial versions, and then there were KH1, KH2, KH3, KH4, so on and so forth. So this was a genesis, I would say, of spying, putting a camera, seeing what others are doing, what's happening on Earth. And we've come a lot far today. And as you can see, this is a black and white image, right? So black and white. So in satellite images, there are two kinds of images. One we do call, in optical images, one do we call as a black and white or a panchromatic band. So when we call a pan image, it's basically taking all the spectrum and it is giving you an image which will have a lot of signal, right? If you break it into red, green and blue, red will have some, green will have some, blue will have some. Each of these bands will not have so much of signal as both three of them combined, right? So this is what it is, panchromatic band, or you can say entire visible spectrum. Right, so this is what the genesis of spying look like, and there have been multiple developments, especially on satellite propulsion as well. So in these days, satellites used to get back to Earth, and so you need to retrieve them, you need to retrieve the films, etc. Once the satellites were put into higher orbits, satellites started to rotate themselves, and once the propulsion was put into satellites, they could maintain the orbit themselves against the atmosphere of Earth, right? And so satellites got developed, sensors got developed, and also optics got developed. Today we have very, very big telescopes inside the images, inside the satellites, that can measure Earth at 30 centimeters. You take a 30 centimeter scale and you can actually see it on Earth in 1 pixel. We'll go through all that. So what I'll be doing now is I will be showing you a couple of examples, okay, of where we are at today. So you have seen where we were in 1972, and this is 2024. Each country has its own capabilities, but the best capabilities you can, very well available capabilities, you can actually see it yourself. Okay, how do you do that? Just go here and go open Google Maps. So on Google Maps, you have data of 20 centimeter. Okay, so go to satellite, and when you zoom in, what you're able to see in the bottom is showing Airbus and Maxar technologies. Now these companies are very, very high resolution imaging satellite companies. They've got satellites with very, very huge telescopes in them that look at Earth, and if you see the resolution, you can see buildings as well. So this is literally 20 centimeter data or 15 centimeter data, whatever it can be, right? So almost, if these are commercial companies, right? So, and these have satellites that are maintained for 5 years, etc., etc. So almost all companies can order data from them, and the resolution that you're able to see on Google Maps, Google buys data from them, processes it, and processes for the whole Earth, and publishes it, right? And as you zoom the data out, you can see the data is actually changing, right? So, and as you zoom in, you actually see that, okay, it is from Airbus and Maxar and etc., etc., right? So this is the interesting thing. You can also go to the Airbus and Maxar website, order these images if you want to monitor something, right? And there are sample data sets out there that you can order and see. But the next point is, these are commercial data sets. There are countries today which have better capabilities than these satellites. Although these satellites are really huge and engineering marvels in themselves, there are countries which can replicate the same satellite with a bigger telescope and can get finer resolution data. So this data is around 15 centimeters to 30 centimeters. There are instances where you can get data for 10 centimeter too. Right? So a 10 centimeter meaning, I think it's my head, right? So you can see my head of 10 centimeter, maybe my head is 15. So you can see even my head as 1 pixel in the satellite images. Limitation here is coming when you take this big telescope and you put it into orbit, right? If you bring that telescope down to Earth, what happens is you can get better resolution. So you can, so this is 30 centimeter data, you bring it down, you can get it to 15, you can bring it down, you can get into 10. But as you bring these satellites down, Earth atmosphere density actually increases, and that actually collides with satellites momentum, and satellites momentum goes down, and satellites want to come down back to Earth, right? So any country that wants to spy basically will develop capabilities to counter this atmospheric density momentum crashing, right? So what they do is, on these big satellites, they put propulsion systems with lots of petrol or whatever you want to call it, and then so what they do is the satellites come down as close as you want to see. If you want to see 5 centimeters, you come down till the telescopes allow you to see at 5 centimeters, and then because once you get your clarity, or once you get your image, whatever you want to spy on or monitor, you get the image, and then because you have to counteract the momentum that is getting down, you fire your engines and go back to your own orbit where there's less amount of atmospheric density, right? So this is kind of like orbital transfer, and there are satellites which do this. So if you want to monitor something, you go down, monitor it, and then again fire and go back. And these are engineering capabilities that are there, and there are companies that are doing orbital transfer vehicles and a lot of things like that. But spy satellites are basically this, right? Today they go down, image, and then they go back up. So this is like for imaging, optical, like your cameras that see this. And I just talked about only one type of images, which are like basically camera type images, right? But then there is like the other side of things, which actually counteracts like lots of defects in this camera type of images. Like if there are clouds, optical cameras do not work. See, because clouds itself are very opaque in optical wavelengths, they will be visible, underneath them nothing is visible. So then what you do is you come up with your techniques like synthetic aperture radar and etc. In 1972, these techniques actually were existing, but in drones and aircraft. But since then we've launched lots of satellites with synthetic aperture radar, and today there are lots of companies which can do very, very high resolution synthetic aperture radar. I'll show you an example of, I think, 1 meter data from synthetic aperture radar, which is from open data repository of a company called Umbra. Okay, let's see that. So what I'm showing to you here on screen is the data from Umbra synthetic aperture radar satellites, and you will be really mesmerized to see how intelligent our technology has become as I actually add Google Maps to this radar satellite, and you can appreciate the difference then, right? So now what synthetic aperture radar does is basically it will send its own radiation and measure the time difference between the radiation sent and radiation received because of the reflections of the objects on Earth, and thereby construct a whole image. In Google Maps types of data or Airbus or Maxa types of data, what you see there is sunlight getting reflected. It can image only during daytime, right? So sun sends radiation getting reflected off Earth. You see it in your telescope, and that is what optical spy satellites are. This is synthetic aperture radar data, which is like satellites sending its own radiation, taking back the radiation, getting a sense of the difference between sent radiation, received radiation, and then making an image structure. So that is how, I mean, if you did a little bit of digital signal processing by seeing the image, one thing you can actually think of is like there's lots of blobs and lots of fringes or that sort that you can see basically coming from frequency domain processing, and this is frequency domain processing artifacts themselves. And I like, for example, let's just go to a river. So let me show you what is the terrain that we're looking at. So this is how the terrain is there that we're looking at, and then we turn on the radar. See, on the ship, this is like a ship, literal ship, right? And see, both of the images on Google Maps and this are captured at different times. So the structure, like the content will not be same, but the whole structure will be same. So there are ships here in the radar data, and wherever brightness you can see is basically coming off of double reflection of the border of the ship and of the wall that is like on the port, etc., etc. So that is how you're able to see this. So this is the one ship that you can see, right? And over here, there's lots of dots. Can you think what it is? If I show you Google Maps, you will understand that these are lots of cars. This is a parking lot, right? So you can see how cars are parked, etc. So this is, let me check what this is, how much meter. So this is like 0.3 meter data. So this is 0.3 meter synthetic aperture radar data, which is very, very fascinating, right? And this, the speciality of this is radar waves or radio waves can actually penetrate clouds, because cloud molecules are smaller than the wavelength of the radar waves. They actually penetrate clouds. So clouds are not visible. Whatever is beneath the clouds is visible. So you can use this radar data in morning, in night, underneath clouds, whatever may be the weather, right? So this is very, very ideal for monitoring. The only thing is you need to make sense of what the radar data is telling you. So you see lots of dots, but you need to have a little sense of what existed there before, and you can actually kind of make sense of what it would be, right? And this is very ideal for maritime monitoring, because in maritime you can see ships very clearly, and here the water is very black, because see, water is the surface. You send radiation, water will directly reflect radiation away from the satellite, so there's no reflected radiation out of the water. So you see black water, but wherever you see noise in the water, like big noises here, these are all ships. This is one more ship, this is one more ship, etc, etc, right? So monitoring is enabled like this. So this is one more example of where the technology has gone, and this is like 0.3 meter 30 centimeter radar data. This is one of the big aspects of monitoring or spying or whatever it is, how militaries use. So militaries use this to observe a lot of different things. This is another really interesting aspect that I'm going to introduce you all, which is communication monitoring. This is like, I have learned this in last 2 years of my life, and this has absolutely blown my brains out. Okay, so what happens is there are communication satellites in geostationary orbits. Okay, and we use our phones, let's say satellite phones, our antennas to talk to this geostationary satellite, and then geostationary satellite sends wherever it has to go. So it is like a data relay. Now if someone sends a satellite to monitor those radiations that we are sending, they can literally do a man in the middle attack in space. And this is little difficult and different type of monitoring. They are monitoring comms, right? And I mean, if you see open source data that is available, there's lots of satellites that do lots of weird things around communication satellites. Okay, like one example I'll give you. I'll show you a photo, and then that will actually make it very clear for you. So on the screen you're able to see star trail images, right? And this is captured by an amateur observer. So as Earth moves, stars move in sky. So you can actually put an camera and leave it for long exposure, and you see stars moving because Earth is actually moving. Okay, but in the middle there are two dots. They are not moving. Your camera is fixed, right? So they are not moving. Thuraya 2 is a communication satellite. Okay, and there's a dot beneath it which is labeled as USA 202. Okay, this object came to Thuraya 2, and it's in geostationary orbit. Okay, geostationary, it's a very, very farthest orbit, 36,000 kilometers away. Came to Thuraya 2, loitered around Thuraya 2 for a while, and then left. Okay, what it does, no one knows. Okay, people think that it is monitoring comms, and if you think so, yeah, it makes sense. And the interesting part here is this is transferable. So if you launch a satellite, geostationary satellite, maintaining it at a geostationary point itself is very, very difficult. The Thuraya 2, maintaining itself at one point is very, very difficult. We need to do lots of orbit keeping. This satellite, which is loitering, goes from one comm satellite to another comm satellite in geostationary orbit. So this particular body, whoever has engineered it, must have large engineering capabilities and lots of propulsion systems on board to do orbit and transfer at geostationary levels. So there are satellite missions called Orion. Okay, and you can read all about it on Wikipedia. It is in open source intelligence that one of the satellite of Orion series is the largest, biggest satellite ever made. Okay, it's not JWST, it's not Hubble, it's not NISR, it's a Spies satellite. And literally, I was shocked to see the antenna length of the comms, spying hardware. The antenna length is 100 meters. 100-meter antenna. Okay. For giving you a little sense of how big the antenna is, I went to Google Maps, measured the length of metro station. The length of metro is around 140. The antenna is literally frigging the length of a metro station. Okay, so that is the actual satellite size. Whoever is sending the satellites, and they are literally moving in space in geostationary orbits from one comm satellite to another comm satellite to another comm satellite. These huge big metro stations are going in space. So today, space engineering is at a very, very different level. We are nowhere at starting point. Someone is building literally metro stations in space, right? And so monitoring and spying is already being done. Space is the next frontier. Now I'm going to tell you the next thing. I mean, this is what is like max, right? But there's literally this another thing. So the satellites that I've earlier told you, the synthetic aperture radar or the high resolution imaging satellites, they are low Earth orbit satellites. As close as you are to Earth, you can build telescopes to see whatever is there on Earth. But the problem with them is they are fast rotating because they are low Earth orbiting. So they'll come over India now, but they'll come over, let's say, Indonesia, or if it is moving this side, Saudi Arabia, etc., they'll move now. So if you want to, consistently monitor, you need to have large number of these satellites. So you build a constellation of these satellites, which is like a huge cost. For building one 30-centimeter satellite itself will take like almost like $1 billion, let's say. You need to build three, you need $3 billion, right? So these are very, very expensive things. And this is like happening because you need to monitor something, right? And these satellites also are agile. So basically you can move the camera here and there, but there's only a certain range. So you can optimize your constellation based on that. But still these are agile and these are dynamic. So someone needs to do all the engineering, right? What if you have a big area, but you want to monitor only that consistently every 10 minutes, every 5 minutes? You cannot invest in hundreds and hundreds of billions of dollars in satellites, right? So now, as I told you, comm satellites engineering has gone to orbital transfer inside the geostationary orbit. The next thing is putting huge cameras, huge telescopes, huge optics mirrors inside geostationary satellite. Today, people are able to image Earth. Like geostationary satellite mean they are always consistently over one place because they are matching the rotation speed of Earth. Okay, like your TV antennas, they are always looking at one satellite only, right? That's a geostationary satellite. So they are building huge satellites, inside them huge telescopes and mirrors to image Earth. Okay, and they are achieving almost 10-meter resolution. And this is like crazy. So imagine you have a CCTV on your country that is imaging almost your country at every 10 meters, whatever they want to image. They are observing everything happening on Earth. They have the capability, right? When I say they, everyone who has this engineering capability. So, privacy, guys, is a myth. Okay. Everything is getting engineered to monitor what's happening on Earth. Let's say this is with respect to governments or whatever it is, because it's like huge budgets, and there are even commercial companies coming right now who are building geostationary satellites and comm spying, hardware and all that. So space is the next frontier. We're doing lots of things in space, and this is where we stand today. And I've told you what information is available public. I have not even touched what is not there in public. So you can imagine what is the state of affairs in space engineering, satellite engineering, and military satellites and all that. I hope I've pricked your interest in military satellites and satellites in general. If you like this stuff, feel free to subscribe to me. My single handle is I am Krish Radha on every social media platform. I'm active on LinkedIn, Twitter, so you can follow me there, and even on YouTube as well.